Okay, so we're going to be focusing on using VSEPR theory to predict the shape and bond angles that are made between the central atom and the atoms bonded to it and the lone pairs that might be on the central atom. VSEPR theory stands for valence shell electron pair repulsion theory. So basically what it says is bonded groups on a central atom and lone pairs on a central atom will repel each other in such a way to make a predictable shape. And I'm going to show you what those shapes are. So let's turn to the next page, and we're going to start with this first group called two bonding groups. I'm probably going to write some stuff on the board as we move along just to kind of help you stay organized. So when we've got two bonding groups, that means you may have singly, double, or triple bonded groups on a central atom. So here in this example, I've got BeCl2, I've got two bonded groups, and we're going to be using the letters A and X to represent central atoms and atoms that are bonded to the central atom. So I'm going to put an A on the beryllium to represent my central atom. And then since I have two bonded groups, these are going to be my X's. Okay, so the designation here is AX2. Now the designation is used to help you get the shape. So anytime you come up with AX2, the shape of that molecule would be linear. Okay, and when you have a straight line, the bond angle is always going to be 180 degrees. Okay, so if I've got carbon dioxide, I would put my central atom carbon and put an A on it. I've got two bonded groups. Doesn't matter if they're singly, doubly, or triply bonded. Okay, that is AX2. It is linear and 180 degrees as well. And then for HCN, I have my central atom. I have my two bonded groups. So these are my two X's. That's also AX2, linear, 180 degrees. You don't have to write AX2 on anything. You just have to write shape. I just use AX2 to help me predict the shape and to give me the bond angle. Does that make sense? Okay, yeah.
On the left, it says bond angle with Lewis structures, so we write 180 degrees on each box.
Yeah, so where you do the Lewis structures, you will, go back and write in the bond angles. Okay? Okay, now let's move on to 3 electron groups. So for 3 electron groups, there are a couple of possibilities. So what I'm going to do is we're going to come down here and I'm just going to address the possibilities here. Okay, so let's take a look at boron trifluoride. So I put an A on my central atom. I have 1, 2, 3 bonded groups. So these would be my X's. My designation here would be AX3, which is not the shape. I use that to get the shape, which is trigonal planar, okay? It is typically deemed inappropriate to abbreviate trigonal, just letting you know, so make sure you write it all out. Now, if I have 3 things in a plane, 360 divided by 3 is 120. So that means this bond angle right here is going to be 120 degrees, okay? Then let's take a look at another example of 3 electron groups. Bless you. Bonded groups, which are my X's, and lone pairs of electrons, which are on the central atom, which are E's. Those can come together to give me my 3 electron groups. So let's take a look at this sulfur dioxide example. I have an A on my central atom. I have 2 X's. This is your introduction to an E, okay? An E is a lone pair of electrons on a central atom only. Don't get carried away and start identifying all the electron pairs on the Lewis structure. Focus on lone pairs on the central atom only because they will repel the other bonded groups. So here my designation is AX2E. Anytime it's AX2E, it's a bent shape. I'm never going to mention that it's angular, okay? And then let me explain the bond angle. Okay. The lone pair of electrons on the sulfur, since it is not contained in a bond, this takes up a lot of space. And this will push away your bonded oxygens more than you would expect it to. Okay, so it looks something like this. So this lone pair of electrons will decrease a bond angle by about 2 degrees. So that means you would expect, since I have 3 things on the central atom, right? You've got 1, 2, 3 things on your central atom. If they were to repel each other equally, you would expect the bond angle to be 120. But since this bond angle pushes away the bonded groups more than you would expect it to, this bond angle is going to be less than 120 degrees. So anytime you guys have got this lone pair of electrons on a central atom, you have to include this less than in front of the bond angle. Okay? Okay, any questions on that? Yeah.
If it's like H2O where there's multiple.
I haven't gotten to that yet. Yeah.
So for like the 3 electron groups, does it like have to be in that shape, or can it be more like this, or like it's like?
There are so many possibilities.
Okay.
Hang tight. I've got a few more.
Okay.
Okay, let's take a look at the next page. Okay, now we can have 4 electron groups, and in comes your water question. So when we've got 4 electron groups, our possibilities are I can have AX4, AX3E, or AX2E2. So let me show you what that looks like. Here I have methane, which would be AX4. Okay, it kind of looks like a jack in space. So my shape for AX4 is tetrahedral. My bond angle is actually less than 109.5, or is it 109.5? It's 109.5. I don't know why I'm thinking less than. There's no E. Okay. Then for this ammonia example, I've got A on my central atom. I have 3 X's, and then I've got a lone pair of electrons, so I'm going to put an E there. So this would be AX3E for the designation. The shape is trigonal pyramidal. Let me explain the bond angle. You know that the lone pair of electrons on the central atom occupies a ton of space. It pushes away the bonded hydrogens, and when it does that, it creates this triangular base between the hydrogens. I'll never ask you to draw this. I'm just sort of explaining where the shape came from. And then you have the top of the pyramid here. That's where they get this trigonal pyramidal shape from. And then in terms of the bond angle, since you have 1, 2, 3, 4 things on the central atom, you would expect the bond angle to be 109.5. But since there's a lone pair of electrons, you would have to put a less than in front of it. So here my bond angle would be less than 109.5. Okay. Lastly, we've got our water example. For water, I've got an A on my central atom. I have 2 bonded groups, so those are my X's. And here's where you have 2 E's present. So yes, for every lone pair on the central atom, your bond angle will decrease by about 2 degrees. So since there are 4 things on the central atom, you would expect your bond angle to be 109.5. But since we've got lone pairs, you would have to put the less than in front of it. In reality, your bond angle is probably going to be somewhere around 105. Okay? All right. Now, we good here? Yeah? Okay. Let's take a look at the next page. These are more advanced shapes. These are shapes that you will typically see in honors or AP. They don't appear as often, but they are here as a reference. So let me explain a couple things here. So here we're going to have 5 electron groups. You will notice that there are 4 different options. I want to make a note because of your lab. Your X's are your bonded groups. And your E's are the lone pairs on the central atom. So when you guys go to fill in the lab, you see where it says regions of electron density? Regions of electron density is going to be the X's and the E's added together. Okay? So it's how many things are bonded or on the central atom. Number of bonding regions, those will be the X's. Okay, and then the number of lone pairs, those will be your E's. Okay, is that helpful? And then when you guys get to the molecular geometry, you don't have to draw it so it looks like the shape. You can just write the shape there. Okay, so that is where you would put linear, trigonal, planar, tetrahedral, etc. Okay, okay. Now, let's take a look at these 5 electron groups. So, if it's AX5 and it's trigonal pyramidal, I'm going to carefully draw this. The top and the bottom group here, these are called my axial groups. And then the ones that are in the middle, these 3, okay, these are called my equatorial groups. If you were taking a Gen Chem class, they might ask you to draw these appropriately. You get this triangular shape between those equatorial groups. If you repel those equally, since they're all in the same plane, the bond angle between here is going to be 120 degrees. Okay, and then you're going to have a right angle between this axial group and this equatorial group. So this is 90 degrees here. Okay. All right, then if you take a look at the next one, this is seesaw. Then we've got T-shaped, and then you've got linear. Typically, it's deemed appropriate to put the lone pair of electrons in the equatorial region when you're drawing those, okay? The one thing that they might mention with this linear one is that the bond angle between the bonded groups, so between here and here, this would be 180 degrees, hence the reason they come up with the name linear. All right, I think that's all I'm going to say about that. Let's take a look at the next page, or the last page, before I let you guys fill in the rest of your lab. Okay, this is 6 electron groups. Here, your possibilities are octahedral, square pyramidal, and square planar. Okay. In terms of the bond angle on the octahedral, this right here is 90 degrees. And so is, this is hard to draw, so is this right here. This is 90 degrees. And then you can see in square pyramidal and square planar, they tend to draw the lone pairs in the axial regions. Something that I'd like to mention to you is sometimes they will ask you about the bonding pairs and the lone pairs and how they repel each other. So this obviously is a lone pair, and this would be a bonding pair. So since the bonding pairs are more contained, I'm just repeating what I said earlier, these bonding pairs would not repel each other as much as this lone pair will with another bonding pair, right? So the bond angle would be expected to be greater between a lone pair and a bonded pair than 2 bonded pairs would be with each other, Okay. Okay. I think that's all we have to mention for the shapes. Is that enough?